Okay, so chapter 3 is great. It's examples of functions. Wow, examples. And so here are the different functions. Okay, so the first of all is the Mobius transformation. It's also called a linear fractional transformation. Okay, if AD minus BC is not equal to 0. Okay, so that's the Mobius transformation. If this were 0, then what that means is that it would just, everything could cancel to like a constant. Wait. And what would happen if it was 0? I think, yeah, everything would, these would reduce. You just have a constant. Okay, so that's the only difference. Okay, so Mobius transformation is what we're after here. And those are interesting. So we'll be looking at that a little bit. Also, this is more Mobius transformation. So the first couple of sections are all this Mobius transformation stuff. More Mobius transformations, and then this is related, and then exponential and trigonometric functions. So the exponential function, so that's like e to the x extended to the complex plane, which would be e to the z, and then logarithms, the logarithmic function. Okay, so those are some examples. Those are important examples in complex analysis for understanding what complex analysis is about. So first, let's start with the Mobius transformation. That's like this. And the inverse is going to be this. So let me show you how that works, or how they come up with that. So you have f of z equals az plus b over cz plus d. Okay, now to find the inverse of a function, what you can do is you can, well, if it's y, then if it's axis, then you change this to a y, right? But y is reserved for something else, so we change it to a w. So w equals az plus b over cz plus d. And then the next thing, if you're dealing with x's and y's, is you reverse the x's and y's, right? But here you can reverse the z and the w. And then you solve for w. So I think that probably every one of you has done this kind of thing with real numbers. Okay, so you distribute the z in, so that's c zw plus c zd equals aw plus b. Then everything with a w in goes to the left, everything without goes to the right. So we have c cw minus aw, and then over here we've got b minus dz. I'm going to change this to a dz rather than a zd. And then you factor w out. And let's rearrange this so it's like negative dz plus b, put it in that order. And then divide both sides by that, and you have this. And then, of course, this is just what the inverse is, the inverse function. Whoa. Oh, this is off a little bit. So what did I mess up?
Just the negative side.
What's that?
If you take the negative side out and put it in the numerator, it'll be just the same.
Yeah.
Oh, I see. Those are the same. I see.
Yeah.
Those are the same. So this negative, yeah, those are the same. They're the same. What am I thinking? I thought this was the same. Okay, yeah. So this is dz minus b, and then this is negative cz plus a, yes. So those are the same. So there's the inverse right there. That's how they calculate the inverse. Another important thing about Mobius transformations is there are some special cases. I want to draw your attention to this, special cases of Mobius transformations. So there's the translation. So z plus b. So remember, the Mobius transformation is this right here, right? Az plus b over cz plus d. Now this is a special case because if you set c equal to 0 and a and d both equal to 1, then you're going to get then this goes away, and this is just a 1, so you're dividing by 1, and that's a 1, so you just have z plus b, right? And then here's another case. So this is translation. Another case would be dilations. This is where you're multiplying by az. So az. So in this case, here you could make b and c both 0, and then make d 1, and you'll get this one, az. And then there's the inversion, which is also really super interesting. That's just 1 over z. So you can get 1 over z by just making a 0 and b 1 and d 0 and then c 1, and you get 1 over z. Okay. So those are 3 special cases. And one reason why those 3 are with those 3 together are kind of important is because any linear transformation can be written like this. So this is basically an inversion, but composed with a translation. This is just this part right here represents a dilation, and this part here represents another translation. Okay, so every linear fractional transformation is a composition of translations, dilations, and inversions. Okay, so let me talk a little bit about those. Spend a little bit of time talking about that. So let's look at, well, there is the dilation, and then here's the translation, right? Okay, so what I like to do is just sort of combine those together, like that, az plus b. And this is going to be, this is a linear. Okay, so you're taking a constant times your independent variable plus another constant. Okay, so that's like a linear function. Okay, and we explore how that goes. So, so I like to combine those together. But let's take a look at these separately. So so let's take a look at the dilation first. So this consists of 2 things. So remember that A is complex. It's not necessarily going to be a real number. It's going to be a complex number. And if A is r e to the I theta, then, well, it's going to be written in this form. it will have the polar form. So if you get it in the polar form, then you can tell pretty much what this does. So if it's re to the I theta, then F is rotation by theta and dilation by r. Okay, so let me give you an example to see what I mean. So suppose we have 1 minus root 3 I z. Okay, and we'll explore what that does. Okay, so all that is going to be your A. Okay, and if we want to graph that, then we go over by 1 in the x direction, or the real direction, and then you go down by root 3I. So you're down there, right? Okay. So this is this forms a triangle. That side is length 1. This side is length root 3, but it's down. So what is your r going to be, and what is your theta going to be for this number?
R is 2.
Yeah, r is 2 because it's a 1, 2, root 3 triangle, or the square root of 1 squared plus this square, which is 3. So 1 plus 3, that's 4. Square root of 4 is 2. What is your angle? This angle here.
5 pi over 3.
5 over 3.
Yeah, negative pi over 3, right? Okay, so that means that this original function here could be written as 2 e to the negative pi I over 3 all times z. Okay, now the way that this works is to graph complex functions, what you typically do is you have a domain plane. So this is a real axis and a real axis and imaginary axis in the domain. And then you also have a range. So you have the domain and then you have the range. So like if you have a function like y equals f of x, then the x-axis represents your domain and the y-axis represents your range. But with complex numbers, you can't do that because in order to just represent a complex number, you need the whole plane to represent all the complex numbers. Okay, and then so you typically make your variables u and v. So this, for the range, u is the real variable and v is the imaginary variable. And you can also say w equals f of z. So we would say we would draw maybe an arrow like that, signifying that you're taking points from there to there. Okay, and so over here we have to have some kind of a set. So let's say that we have, let's say that we take, I don't know, there's a lot of stuff we could do. Maybe a circle. How about we take this circle from, we'll say that's 2, and this is the origin, and then let's say that is centered at 1. Okay, so this would be In fact, maybe we can just take the whole circle, everything inside. So we could say this set is the modulus of z minus 1 less than or equal to 1. So that's a circle of radius 1, and the center is 1. And then say, what happens to that circle as we take it with under this linear transformation, which is this? Well, what's going to happen is this 2 right here is going to double everything. So what will happen is that this 2 right here will go to 4. This 0 will stay where it is, because if you multiply the 0 by 2, you're still going to get 0. And these points right here are also going to expand out, double. So anything is going to double in size. Okay, and then this part right here, the e to the negative pi I over 3, that's going to rotate it to an angle of pi over 3. So if this is pi over 3, this goes out 2. We're going to take this radius all the way to 4. So that's going to be 4. And then the 0 will stay the same. And the one thing that's really nice about Mobius transformations, which we'll learn later, is that if you have a circle or a disk and you map that using a Mobius transformation, that's going to map to either another circle or disk, or maybe the outside of the disk or something. Circle will map to a circle, but it also could map to a line. Okay. But if we have a linear function, then circles are going to go to circles. Okay. And disks are going to go to disks. So basically, this point right here will still stay at the origin. This point is going to go to here. And we can figure out what that point is if you want. It's going to be 2e to the negative pi I over 3 times z. But probably it's probably better to just dang, everything froze. Oh, here we go. Okay, so where are we? That point's going to that point. So you could plug the 2 into here, but you're also going to plug it into the original one. So that's just actually going to be 2 minus 2 or 3i. That's probably easier to do. And then the rest of the circle is just going to fill in. The center is going to be right here now. And the rest of it's just going to fill in. So you're going to have a circle like that. And then the inside is just going to map all to the inside. Okay. So the important thing it's rotation by that and it's dilation by r. So here r was 2, but if r was say 1/2, then everything would be cut in half, right? Everything would just be cut in half. Okay. So that's how that works. So this is this one, and then it's also typical to write down what it maps to. And this would, in terms of W, so instead of the Z, we have W. Now we want to describe this circle here. And that circle is going to be, well, 1 is going to map to, the 1 is the center of here, and that's going to map to 1 minus 3i. So this will be W minus 1 minus root 3i. And then the radius is going to be 2. Less than or equal to 2. So that's the center. And then the radius is 2. So less than or equal to 2. Right there. So this maps to that. Okay. So there's that example there. Let's take a look at this one right here now, next. Which is the translation. Okay, so this is translation. And let me just give you an example. What this does is it keeps the, if you're mapping a shape or a set of points, it keeps the same shape. It just moves it. It just translates it by whatever B is. And again, B could be a complex number. So you could have Z plus 2 minus 3I, for example. Okay, so you could have that. And what it would do, like let's say that we had, like let's just go the same thing. So we have, let's say we have the circle of radius 1 right here. No, that's a 2. And it's centered at 1, right? So we have the center at 1. So let's just take the boundary, okay? So what's going to happen is the plus 2 is that's going to shift it up by 2. No, to the right by 2. And this is going to shift it down by 3. So this is the real part, which is the x-axis, the real part. And this is the imaginary part, which is the y-axis. So that's up and down. So this will shift us to the right by 2, and this will shift us down by 3. So if we take the point 0, for example, that's going to go to 2 minus 3I. Okay, so let me mark this point with an X. That's 0. That's going to go to here. This 2, I'll mark that with a red X. The 2, that's just going to go to 4 minus 3I. That's going to go to here. And this 1 in the middle is just going to go to the middle, although that's not part of the circle. That's not part of the circle. It's just a reference point. And then everything else is just going to go as you expect. So this upper part of the circle is just going to go to the upper part here. And the lower part of the circle is just going to go to the lower part here. Okay, so that's just that's a translation. Okay, let me see how much space we have here. Oh yeah, not much space left. Okay, now you could also put these all together. So if you had something like this, let's say we had 2 minus 2I, Z, plus 3 plus I. Okay, so that one, this, if we put this in polar coordinates, that's 2 root 2 is the radius, and e to the negative pi I over 4. That's all times Z, plus 3 plus I. Okay, so what this would do, if you have this function here, is you start with what's right here. This is what you do first, and then you do this part. Okay, so first you're going to magnify by 2 root 2. So that makes it bigger by a factor of 2 root 2. And you're going to rotate by negative pi over 4. So that just goes through an angle of negative pi over 4. And it doesn't really matter which of those you do, because those are interchangeable. If you magnify and then rotate, it's the same as rotating and then magnifying. But it does make a difference. It is important to do these first, though, because that's right next to the Z. And then the second thing then it's going to be this translation. Then you're going to shift. And what does the translation say? The 3 plus I. What does the 3 do?
Right 3.
Is it for the right?
Yeah, right by 3. And the I?
Up by 1.
Up by 1, right? So right by 3 and up by 1. Okay, so that's how you would handle something like this. Okay, now the other one that's really cool is the inversion, the 1 over z, and figuring out what that does.
Rotation.
Okay, this one is like, you could also rewrite this here. So if z is r e to the I theta, like that. So I'm kind of going a little bit back. So this would be like the variable r and the variable theta, not like but before what I said they're constant, and it's part of the coefficient. So this would be like the variable there. You can kind of look at it like that way, and then so this 1 over r is like right there, and then e to the I theta, that's in the denominator, is the same as having an e to the negative I theta in the numerator. Okay, and if you wanted, you could go, we could put that r e to the negative I theta there, and then we would have r squared in the denominator. Okay, so 1 over z is the same as this. Okay, now, do you guys recognize what the numerator is? R e to the negative I theta. Does anybody recognize what that is?
Is that E?
In terms of z. What's that? It's okay if you don't recognize what it is. It's the conjugate, actually. And then R, but you guys don't know what R is, the modulus, right? That's the conjugate. So there's, let me just do a little aside right here. So let's say you have a complex number right here, right? Here's z. And that's, we'll say that's r e to the I theta, right? And so this is your theta, right? But let's say it's also say it's x plus iy. And then, so then this is x and that's y. Okay, so what's the conjugate? If you're looking at this part, the conjugate is x minus iy. And then if you, on the graph, you're going over x, but instead of going up, you're going down, right? That's minus y. So here's the conjugate. Okay, but what's this angle? What's that angle there?
Negative theta.
Negative theta. So this is really, and then the radius is still the same, right? So the conjugate is r e to the negative I theta. So you just, if you just flip the sign on the theta and leave everything else the same, you're getting the conjugate. Okay, which is what we have right there. So that's the conjugate right there. And then r, of course, is the modulus, or the length, or the magnitude. And then r squared is the magnitude squared, right? So 1 over z is actually equal to this. So if you look at it in that way, then it can help you tell what's going to happen. Okay, so let's look at it this way. For reference, I'm going to draw the circle of radius 1. Okay, so I'll put that's 1, that's I, negative I. I'm not really going to use this. I'm just going to draw it for reference. Okay, so now we're going to pick a few points. Let's start with this first value right here. This value right there. And we're gonna take these points and we're gonna map them under the reciprocal transformation mapping. And then so over here we have the image. Okay, what happens to each of those points? Okay, so let's start with this guy right here. Basically, its magnitude is all this, right? This length right here represents the magnitude. And if the magnitude if this is 1, then maybe the magnitude is 2, right? Maybe the magnitude is 2, which means R is 2, right? So in the image over here, if we take 1 over Z, what's the magnitude going to be over here? If the magnitude here is 2, what's the magnitude going to be over here when you take 1 over that?
1/2.
Yes. So whatever the magnitude is here, it's 1 over that. So if the magnitude's 2, then this is going to have magnitude 1/2. So it's going to be somewhere along this inner circle here. Okay, and if this is Z, the conjugate of this is down here, right? So it's actually going to be on the same line as the conjugate would be, but the magnitude is going to be 1/2. Okay, so you see that? So it's going to be down there. So on the same line of this angle right here, but the negative of this angle, like if that's theta, that would be negative theta. Okay, so bottom line is this point goes to there. Okay, that point goes to there. Okay, let's choose another point. Let's choose a point over here, right there. Okay, so I wish I could let you guys draw on this, because how do we figure out this point, where this point's going to go to? First of all, the magnitude is, let's say the magnitude is 1/2. So what's the magnitude going to be over here?
1/4. I mean 1/4.
No, you don't divide by 1/2. You take the reciprocal, because this is 1 over, right? So if the magnitude is 1/2, okay, then what's it going to be over here?
2.
It's going to be 2. Okay, so it's going to be out here in this outer thing, and then which quadrant is it going to be in over here? First, second, third, or fourth? Third, right? Because the conjugate's going to puts it down there, and then you magnitude it out. Okay, so it's going to be actually right over here somewhere. So that point's going to go to there. Now, other interesting things is if you let's say we take the unit circle here, and we'll split it up into, let's say we have this region and that region. Okay. So the question is, what's the blue region going to map to? Which quadrant will it be? First of all, the blue region.
4.
The fourth quadrant, right? So the fourth quadrant?
Yeah.
And it's actually going to be everything outside here, right? It's going to be everything outside. Okay, and then the red is going to go to where?
First.
The first quadrant, right? So the red's going to go to the first quadrant, and it's going to be everything outside there. Okay, and then if we had, let's say we had this region here, all this, in the third quadrant, where's that going to map to?
The second one.
Yeah, the second quadrant inside here, right? Inside there. An interesting thing. Now, one of the things that one of the things that we say in complex numbers is that infinity is, you think of infinity as a point. Okay, so just think of infinity as a point from now on. I mean, maybe you've been told it's not a point all your life, but maybe you were told a lie because it is a point now in complex variables. And we do think of it as a point, like other points. And if you take the inversion transformation maps 0 to infinity, and it maps infinity to 0. Okay, so then that makes things work out really nicely. Okay, now page 36. Theorem 3.4. So this is an interesting thing that will help you understand how to do these mappings better. And that's this principle right here, that Mobius transformations map circles and lines into circles and lines. That's Mobius transformations. Okay, so later on we're going to be studying other transformations, and it might not work out that way. But with Mobius transformations, if you have a circle or a line, it will map to another circle or a line. Also, you can think of it, a lot of mathematicians think this way. They think, okay, lines are circles. Okay, so a line is a circle. And so you think, and the way that you justify that is that if you, so you have a line right here, it goes forever. And what happens is you go along the line, and then somehow you hit infinity, and then you're over here, you're coming back this way. Okay, so you go along, so you go that way, hit infinity, and boom, you're over here, and you're coming back to the original. So that's kind of how a circle behaves, right? You're going around, and you hit the same point, and then you go around again. Well, that's kind of how you could think lines behave a little bit. So a lot of mathematicians will say, oh, lines are circles. And then you can just say, oh, Mobius transformation maps circles into circles. And then everybody's like, oh, okay, yeah, we'll go with that one, okay? So those are two ways that you can think about this. Let's talk a little bit more about infinity. So if infinity is going to be a point, then we have to come up with how do we handle limits near infinity? And first of all, the way we handle limits in general is, let me just review a little bit, maybe on the, I'll review on the previous page. So the way that we handle limits in general is, let's say we have the limit as z goes to z naught of f of z equals w0. Okay, so we have that limit right there. Okay, so the definition is given epsilon greater than 0, there exists a delta greater than 0 such that z minus z naught implies this, less than epsilon. Okay, so now what makes this work is that in the, you have a, again, you have, let's look at it from this point of view, where you have, this is the domain, and this is the range. Okay, what makes it work is that this one is what we call a neighborhood in the domain. So it looks like this. So it's everything inside a disk like that. The radius of that disk is delta, and it's centered at z naught. And then this one is a disk over here in the range, plane. Okay, and it looks like that. So essentially, what this limit is saying is that you can find a delta that's small enough. So given any value of epsilon, so you're determined over here what the epsilon is, okay? You can find a delta small enough so that every single point in here maps to a point in here. With the exception of the z naught, the center point, which might be undefined. It was typically undefined because that's where things are interesting, where z naught's undefined for the function. So that every single point in here maps to some point in here. Okay, and then that's how you get this, how you get the limit. Okay, so this is called a neighborhood. Of z naught. And this is called a neighborhood of epsilon. Okay, and then that's how that works. It's in terms of like neighborhoods. So here, this right here, if you take that, this is a neighborhood of infinity. So neighborhoods of infinity actually look like this. So n is typically some really big number, a really huge number. And that's n. And then, so then you're going to have like this big disk here. And then a neighborhood of infinity would be everything outside this disk. Kind of a big neighborhood, right? But that would be a neighborhood of infinity, everything outside that. And so you can make kind of what you might consider a smaller neighborhood, although probably it's going to be the same size, by making this n larger. Okay? And then also something like this is also another neighborhood. You're just using an m instead of an n, right? Although in this context, this is more like a condition on the z, okay? This is also another neighborhood of infinity. Okay, so in the definitions, whenever you have, like if infinity appears over here, if infinity appears over here, you replace that part with this. You replace, okay, so if infinity appears right here, you replace this with you replace this with this. And then if infinity appears right here, then you replace this with this. Okay, so if infinity appears there, you replace this then the other part with the deltas gets replaced like this. And then if they appear both places, then you replace both. So if the epsilon is replaced with, so if infinity appears here, then the epsilon's replaced with this, and so on. Okay, so that's how that works. And then infinity has these properties. So with the point infinity, it's called the extended complex plane, which is the union of the complex plane with infinity. And then these are the properties. If you add infinity to any finite point, you're going to get infinity. If you take something times infinity other than 0, then you're going to get infinity. Infinity times infinity is infinity. A divided by infinity is 0. You divide by infinity, you get 0. And then if you take and divide by 0, you're going to get infinity. So that's how the Mobius transformation works right here. It takes 0 to infinity. So like 1 over 0, that's infinity. 1 over infinity, that's 0. So that's how that works. Another way to look at all this is with something called the Riemann sphere, or the complex projective line. So the way that works is, or a stereographic projection. So here, imagine that there's a table that extends in infinite many directions. Okay, so imagine that this is a table right here, and it extends in infinitely in all these directions, right? And let's say this is a basketball, or whatever your favorite sport is, and it has a ball. Pretend that that's a basketball lying on the table. And the idea is you come up here to the top of the ball, right here. And this is called, the top of the ball is called the North Pole. And that applies at 0, 0, 1, where z is 1, x and y are 0. And then the bottom of the ball, which makes contact with the plane, is the South Pole. Okay, so the North Pole is up here at the top, and the South Pole is at the bottom. Now, the North Pole is perhaps you could say, is the important one. Imagine this right here, this plane here, or the table, is the complex plane. Imagine that's the complex plane. Now, every single point on the ball, besides the North Pole, if you start from the North Pole, let's say you have a point right there. Okay, you choose any point on this plane. Okay, if you connect the North Pole with that point with a straight line, then it will intersect the sphere at some point. There'll be some point where that intersects with the sphere. Okay, or maybe the point's right here. And so then you come down here and it intersects at some point, like maybe right there on the surface of the sphere. Okay, and maybe the intersection's right there, right there, right? So it intersects. So every point, any point that you choose down here on the plane, if you draw a line from the North Pole through the surface of the sphere, it'll correspond to exactly one point, right? So every And then if you draw straight down, that's just going to be the south pole, and it's going to intersect right here. Okay. So every single point in the complex plane is associated with a point on the sphere. And then the North Pole, though, is not associated with any point in the complex plane. But as you move on the surface of the sphere up towards the top, then the points that, then the line that you draw through the North Pole on that point is going out further and further onto the complex plane. And the limit of that would be like infinity. Okay, so basically infinity is going to associate with the North Pole on the sphere. Okay, so let's see here. The next thing is okay, so the next thing is what we call the cross product. Okay, or the cross ratio. I'm sorry, cross ratio. Okay, so this right here is the cross ratio. And essentially what it does is this is going to be, so note that there's a z there and a z there, right? And then everything else is just a constant. Z1, Z2, Z, and Z3 are three different complex numbers, but they're fixed. Now, what happens? So this right here is called the cross ratio, but it's a Mobius transformation. Okay, so let's call that f of z. We'll call it f of z. Now, and then z1, z2, and z3 are specified numbers. Okay, so that if you plug in z1 into this expression, then what are you going to get? So you're plugging in a z1 here and a z1 there. What's that?
0.
You get 0, right? Because that's z1 minus z1 up right there. That's going to be 0. So that's going to be 0. Okay, if you plug in z2, what are you going to get?
0. Oh no.
What? So we plug a
1.
z2 in right here. So we can write it out if you want.
It's gonna be 0. Since the
It's going to be,
denominator will be 0.
It's going to be 1.
0?
Yeah.
Wait, none of these, this is z2, okay, this is z2 minus z1. I guess I wrote that wrong. That's z2 minus z1. Oops. Can you simplify that?
Okay.
Yes,
Can
you
be
can
one.
cancel it out. So C 1, it's just going to be 1.
These guys cancel, right?
Yeah.
And then these guys also cancel.
So it's gonna be 1.
Or, yeah, that's going to be 1. So, or probably the more appropriate English would be that they reduce to 1. So f of z2 is 1. What about f of z3? You put a z3 right there.
It's 3. And then
Then you have z.
It's still gonna be undefined.
Infinity? Yeah, so you have a 0 in the denominator. When you get 0 in the denominator and there's a finite number in the numerator, then that's going to be infinity.
Okay.
Okay, and then yeah, so here's actually the 3 statements like that. Okay, now So that's how that works. Now, if so what you can do is you can use this to do almost any mapping. So like, for example, well, first of all, you can do it this way. Let's suppose that we want, let's choose 3 different points, okay? And let me see here. Let me write down the cross ratio just for reference right here. Okay, so let's say here we have the cross ratio. And so let's suppose we're given a problem and we're supposed to find a Mobius transformation. That maps, well, give me any 3 points. Dang, I can't call any, I can't say any names. Just give me any 3 complex numbers.
Just like 3i plus 2, like that.
Yeah, maybe not that complicated. And maybe I should just choose it. No, I'll choose I and 1.
0.
Okay, so we have those 3 right there. Okay, so what we want to find a Mobius transformation that maps this one to 0, and that one to 1, and that one to infinity. Okay, so we can write it down here. Maybe with a big sign right there. Okay, we can basically just write it down by just making this one Z1 and that one Z2 and that one Z3. So this becomes, you carry the Z over, right? Minus 2 plus 3i. This one right here becomes this minus this, I minus 1. This right here becomes Z minus 1. And then Z2 minus Z1, that would be this minus that one. So we get there. And then if we simplify that, then we'll have a Mobius transformation that does the mappings that we want. Okay, also, what you can do, and we don't have much time left, but let's suppose, so here's another example. Let's suppose that we have 3 points and, well, actually, let me do this first. Okay, let's suppose that we have, so the 3 points for the Mobius transformation were 0, 1, and infinity, right?
Mm-hmm.
So, but let's suppose we want to do this. We want to map 0 to I, and we want to map 1 to 1 plus I, and we want to map infinity to, let's say, 4, something like that. Let's say we want to do that. Now, the cross ratio is going to, if we use this Z1, Z2, Z3 in the cross ratio, then it's going to map I to 0. And it's going to round back to 1. It's not 4 to infinity, right? But so if we plug those numbers, if you plug these numbers into Z1, Z2, Z3, that's going to give us a cross ratio that will map that to that, that to that, and that to that. But if we wanted to go the other way, then what do we do? What can we do with this result here that will make it go the other way?
The inverse.
Yeah, the inverse, right? Wait a minute. Oh, plus 5. Yeah, we just take the inverse of this, whatever it is, right? And that will go the other way. Okay, so this is probably a good place to stop. Actually, we're out of time. And this is also a good place to stop. Any questions about anything before we let you guys go free for the weekend?
Wait, you said that was the inverse, right?
No, this is this function right here. Yeah, this is the inverse of what we want. So to get this, oh yeah, I should probably specify. If that's f, then f inverse of z is going to have these properties. Okay, so we would have to do another step and figure out how to find the inverse, right?
Yeah.
Yeah.
Okay.
Yes. Then the next step is to find any 3 points going to any 3 points, and then we use this idea to come up with 2 different functions and take the composition. But we'll talk about that next time.